Thank you for the introduction. So I'm Alex Marcus. Today I'm going to talk about locating contours of functions leveraging multiple information sources. So this was developed with Remy Lam, former MIT, now at DeepMind, and Professor Karen Wilcox from UT Austin. So our goal here is to construct a classifier, but instead of having a discrete set of labels, we actually have a continuous function, and some specific contour of this function divides the domain into different classes. So for instance, here we have a function that characterizes the stability of a dynamical system. So the zero contour of this function divides the domain into regions where the behavior is stable and unstable. The challenge here is that normally obtaining this contour, an estimate of this contour, requires many function evaluations. And doing these evaluations in some problems is very expensive. However, in many cases, we also have access to other sources of information that provide relatively cheap information about the system in the form of some biased estimate of the expensive function. So the question that we wanted to answer here is how can we leverage all of these information sources to produce an accurate classifier at relatively low cost? And our answer to this question is an active learning algorithm that uses a Gaussian process surrogate to fit data coming from all different sources simultaneously, and that learns the correlations between the different sources. So we use this information to select new evaluations, so where to make new evaluations and which model to evaluate next. So here I'm going to show an example of comparison of the performance of this new algorithm, this multi-information source algorithm, which is shown here on the right. So we have here three information sources, IS0, IS1, and IS2. And we're going to compare it to a standard active learning algorithm with a single information source, which is shown on the left. So I'm going to show the estimates of both algorithms at the same cost. And we start both algorithms with 10 random samples. So at the time that it takes to have a single IS0 evaluation for the single fidelity, single information source algorithm, the multi-information source algorithm decides that it's much more informative to have several evaluations of the cheaper information sources, and uses that information to have a better estimate of the contour that we are trying to locate. And just at the cost of one more IS0 evaluation, we basically, the multi-fidelity, multi-information source algorithm has basically nailed the estimate of the contour, whereas the single information source algorithm is still kind of struggling to have a good estimate. And as we progress the evaluations, what we see is that the multi-information source algorithm is basically using the cheap information sources to explore the domain in an intelligent fashion, and just using a limited number of IS0 evaluations to pinpoint the accuracy of the estimate. Whereas the single information source algorithm doesn't have a choice. It has to do some sort of exploration of the domain using only expensive IS0 evaluations. So eventually we'll get there, but it will take a much longer time to have a good estimate. So the contributions of this paper are threefold. So the first one is we introduced this concept of contour entropy, which is a rigorous measure of the uncertainty about the location of the zero contour of a function approximated by statistical surrogate. The second contribution is a decision mechanism in which we use our Gaussian process surrogate as a generative model to estimate an expected reduction in this contour entropy for a given evaluation. So we use that to estimate what is the evaluation that is going to lead to the most reduction in contour entropy per computational cost. So we select both where in the parameter space to make the evaluation and which model to evaluate it. And then we put it all together in the algorithm Clover, which combines data from multiple information sources to locate contours of expensive functions at relatively low cost. So with that, I'd like to invite everyone to come to the poster session and talk to us. This is poster 99. Thank you.